Thanks for coming by to see our poster. In this poster, we want to address the aleatoric variability or natural variation in rupture location over the 100-meter length scale based on a formalized analysis of past paleoseismic trenching studies. The idea is that there's so many trenches that are dug, both for research and for consulting, that we might use the exposures of the fractures in them to understand the width and intensity of deformation associated with active fault zones, and also to try to understand the variation in total versus maybe compared to the most recent earthquake, and to look at the variation as a function of fault slip type, fault slip rate, recurrence interval, materials that are being ruptured, other contexts. And so what we've done is we build on work that was prototyped by Chen and Dawson and Wills at California Geological Survey, where they went through and manually examined more than 100 trenches. And so in this case, what we've done is built a MATLAB tool that interactively allows the operator to accumulate information, basically metadata about the trench log and the site, and also decisions made during the digitizing, and then to basically georeference or at least scale the trench log, and that's shown in step 5 below here, where we set the scale. Then we can review sites. So, for example, in step 3, we identify the geologic unit, the indicating landforms for this trench site. Was there, in this case, the example, there was a ridge and also an offset channel, so it's very well indicated by tectonic landforms very nearby. The other thing we do is we try to systematize our lithofacies. So it's a little bit small to see in this video, but these codes, like SH, GH, that would mean horizontally stratified sand and horizontally stratified gravels, give us a systematic way to record the materials. And then we just start clicking out. And so we scale it, then we identify the ends of the trench, then we identify the primary fracture, so that's the red dot with the circle. Then all the other fracture tips are digitized as the red dots. And if we can, we go back through and identify the most recent earthquake fracture tips to basically compare the cumulative versus the most recent event. Um, then, and so we can, in this example, we've done 10 trench walls or 5 trenches from the Bedard site along the San Andreas Fault in Central California, and have a histogram of things like trench length, trench half width, so kind of distance, the longest distance from the primary fracture to one of the trench ends, fault width, then a fault half width, same thing, longest distance from primary fracture to the end of the fracturing. We can also compare the most recent rupture fracture network relative to the cumulative one by getting the maximum distance to any fracture. So that gives us a sense of how narrow versus how wide the most recent rupture was. And also we can get fracture density. And so in this case, I also show an example the from Pamir frontal thrust, which is a beautiful set of reverse fault trench logs in Central Asia. And so the idea here is to show what we're up to and seek some ideas from the community. What do you think? Does this make sense? Do you have suggestions? Because also these trenches that I'm showing as examples are research logs, and so they're pretty narrow and very detailed logging. They're not consultant logs where maybe there's a little bit lower level of detail, but there might be much broader because they're looking to establish or not the presence of an active fault. So we want to have a greater variety of input data as well. So love to get any input from people either in person at the meeting, or please leave a message. Let me know what you think. And if you want the MATLAB, you're welcome to have it. It's nothing fancy, but just tries to make this process a little bit more objective and a little bit more efficient. Thank you.